Okay, so I think it's good time to start. So myself, Harish, I am here for the live interaction session of Algebra second course. So in the last session, we have seen, so my voice is audible, right?
Yes,
Okay, so I will share the screen. Yes. So in the last session, we have seen till problems 6 of assignment 6. So yeah, so today we will start with the problem number 7. So this is, let me just change the color. Yeah. So it's week 9. Is 22nd March, I guess. Yes. So we have seen some problems of assignment 6, and we will first continue with the remaining problems of assignment 6, and if uh, we will try to finish assignment 7 also. So yes, I will just uh, paste question number 6 here. Okay. Yes, so it says let k be the field adjoining omega to q, and L be the field adjoining third root of 5 with q, and F is the base field, that is q itself. Omega is the third root of unity. So we have to choose all the correct options. So first option says that the field KL. So I have already defined in the last lecture what was KL. So KL is the smallest field containing K and L. So it's a the first option says that KL over L is a Galois extension. So just as a recall, so a Galois extension is an extension that is normal and separable. So normal means it is the splitting field of a certain collection of polynomials, and separable means for each element, the minimal polynomial of that element have distinct roots in any extensions, in any extension of the field. So yes, so in the notes we have seen one corollary. So I will just mention that corollary, and this question will follow from that corollary itself. So let me just write the corollary first. So corollary. So it says let k l, let f k l, which are subfields of C, and f is contained in k intersection L. Also, one has to suppose k over f and L over f are both finite Galois extensions with k to be ought K upon F, just a moment. So I think I just by mistake copied the wrong question. So uh, till 6 we have done. So from 7 we are supposed to start. Let me just paste the 7 question and continue with its solution. Sorry for the confusion. So, yes, this is a question for from which we have to start. So 6th question we have already discussed in the last interaction session. I just saw that. So yes, so that corollary is also not needed. That would be required in the at the end of uh, maybe for problem 8 we need that. So let's not bother about it. Yeah. So let's start with the problem number 7. So it says that fx is the fourth root of so fx is x4 minus 2 be the polynomial over the field q and k be the splitting field of fx over f. So we have to choose the correct options. First is k over f is a Galois extension. So this is easy to see. We have already seen such questions. So why it is normal? Because uh, k is the splitting field of fx, right? So if it's a splitting field, so it's normal and separable because uh, characteristic of q is 0 and k over f is an algebraic extension. So that makes it a Galois extension because it's normal and separable, so it turns out to be Galois. Now, what is the degree of k over f? So consider the correct answer is 8. Let us see how. So consider the tower of fields, following tower of fields. K to be, so we have K as so it's a splitting field. So what is the splitting field of this polynomial? So uh, it's the field that contains all root of x4 minus 2. So it will be the field adjoining fourth root of 2 and iota with q because the roots of this is since the roots of x4 minus 2 are uh, fourth root of 2, fourth root of 2 uh, minus fourth root of 2, fourth root of 2 iota, and minus fourth root of 2 iota. Okay. So, yes. So, this is an extension of the field Q with fourth root of 2 and Q. So, uh, So the degree of this extension is 2 because iota satisfies x square plus 1 over this, and iota is not inside this field. So it is 2, and this is 4 since x4 minus 2 is irreducible over q, and cube root of fourth root of 2 is will satisfy this polynomial, and it is irreducible over q, so it turns out to be the minimal polynomial. So this implies that is your f. So k over f has dimension 2.4, that is 8. Okay, so that's why the dimension is 8. Now let's, I hope there is this is clear. I will move to the next question. This would be required there, so I will keep it this here. This we will require for question number 8. Let me just quickly paste question number 8 here. So it says that K, L, and F be the subfields of C such that F is contained in the intersection K intersection L, and suppose K and K over F and L over F are finite Galois extensions such that automorphism group of K over F is non-abelian and simple, and automorphism of L over F is abelian group. Then we have to choose the all correct options. So as I said, that we require this corollary. So the corollary says that F, K, and L be the subfields of C, with F is contained inside K intersection N, and suppose K over L and L over F are both finite Galois extensions with a automorphism group of K over L, K over F is non-abelian simple, is non-abelian. This is the corollary discussed in lecture notes. So you can refer the notes. Okay. So K over F is non-abelian, simple, and B is automorphism group of L over F is abelian. Then first L intersection F is F. Second, out of KL over L is isomorphic to out of K over F. And third one that it says is out of L over F is abelian. So this is the corollary that is being discussed in the lecture notes. So you can see that it matches with the assumptions in the question. So K, L, and F are subfields. F is containing K intersection L. K over F and L over F are both finite Galois extensions, and automorphism of group of K over F is non-abelian simple. Automorphism group of L over F is abelian. Then we have to choose the correct options. So first one is L intersection maybe here L intersection K. You were saying something? Last time the was open. Khyati, you are saying something? Okay. So, okay. So, uh, yes. So here I made a small mistake. Here it should be uh, K intersection L is F. So here it is K intersection L is F. So you can see that it matches with the uh, so the assumptions in this corollary matches with the assumptions in the question. The assumptions in the given problem. So thus say this is first, this is second, this is maybe the third, and this is fourth. So automorphism KL over L is just proper subgroup of uh, morphism of K over F. This is uh, not true because this is isomorphic to this. So first and fourth options are not correct, because in the fourth option it is saying F is not equal to K intersectional, but it actually this is equal to K intersectional by this corollary, and KL over L is isomorphic to automorphism of K over F. This is true by this condition, and KL over L is a normal extension. Uh, this uh, we have to see maybe. So there was oh so in so this is the assumption part. The third in the conclusion there was three parts. First is K intersection L equal to F. Automorphism of KL over L is isomorphic to automorphism of K over F, and this is KL over L is a normal extension. So this is same as the third option. So you can see the second and third are correct, and first and fourth are not correct. Thus first and the fourth are not correct, and second, third are correct. Okay, so this is just a direct consequence of that of the corollary discussed in the lecture notes. So there is nothing to be done. Uh, so we have just used the make use of the corollary. Okay. Okay. So I hope that is clear, and we can move to the next part.
Yes.
Okay. So So next option says that if K is the field Q adjoint with root 2, L is Q adjoint with root 3, and F is the base field, then you have to choose the correct options. So first is KL over K has dimension 4, KL over L has dimension 4, and KL is just Q adjoint with root 2 plus root 3, and the fourth one is K and L are both radical extensions over F. So I have already defined what is a radical extension. Uh, so I will just recall it when we come to option 4. But let's first consider the tower of field. So F is the base field, that is Q. Then you have K here, which is Q adjoint root 2, and here you have L, Q adjoint root 3. So and then KL is the smallest field containing root uh, K and L. So K is Q adjoint with root 2, means K is the smallest field containing Q and root 2. This is the smallest field containing Q and root 3. So KL will be Q adjoint with root 2 and root 3. So this is the smallest field containing root 2 and root 3. And we have we know that this part has dimension 2. Why? Because we have already seen that root 3 is not inside. Oh, root 2 is not inside Q root 3 in one of the problem, and root 2 satisfies x square minus 2 over L. So it is not inside this field, so its dimension has to be greater than equal to 2, and uh, it satisfies the degree 2 polynomial, so its dimension is exactly 2. And then root 3, this we already know that this has dimension equal to 2. So this implies so KL over F has dimension 4, KL over L has dimension 2, and similarly you can see that this for this part also dimension is equal to 2, because similarly root 3 does not belongs to Q root 2, so it's outside this, so it cannot be the same KL and K. So and the minimal polynomial that it satisfies is of degree 2, so the dimension has to be precisely 2. So KL over L is of dimension 2, and KL over K is of dimension 2 again. So uh, this implies that this option is not correct. This is also not correct. And in one of the exercise problem, we have already seen that uh, we have already seen in earlier assignment problems that Q root 2 root 3 is same as Q root 2 plus root 3. So this option is correct. And K and L are both radical extensions. This is also correct, because what was the definition of radical extension? It radical extension means so something is called a radical extension of some other field if uh, for each alpha in K there exists n such that alpha raised to n belongs to L. So you can see for, so for q it contains elements q. So for all q you have the n to be 1, and for root 3 you have n to be 2. So root 3 square, that is 3, will be inside this q, and same here, root 2 square, that is 2, will be inside this field. And any element of q root 3 is of the form a plus b root 3. So for that also you can check that if you square it, then you will get something, and then if you again square it, then it will be inside this field. So any element of so basically we define what is a simple radical extension. So it was an extension of the form some q adjoint alpha, such that alpha n is inside q. That's called a simple radical extension. And uh, here, since alpha is root 2 in case of L, sorry, in case of K, and root 3 in case of L, and square of both of them are inside this Q. So they are just the radical extension, simple radical extension of F. So last option is also correct, just by the definition of simple radical extension that we have seen. Okay. So with that, I will move to the next question, if that is fine with you.
Yes.
Okay. So that's supposed to be the last question of this assignment. And okay, so it's saying consider the following two statement. First is let p be a prime and phi p of x is the cyclotonic polynomial uh, that is just a second. So yes, so it's the cyclotonic polynomial for p prime is xp minus 1, xp minus 2, and so on to x plus 1. So that we have seen in lecture notes, that this is the cyclotonic polynomial for phi px, and 257 is of the form 256 plus 1, which is 2 raised to 8 plus 1, and any Fermat prime is of the form some 2a p1 p2 dot 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 pn. Oh, sorry, it's not Fermat number, it's Fermat prime. So any Fermat prime is of the form, it is of the form 2m plus 1, and here you can see 256 is also of that form, so it's a Fermat prime. So both 1 and 2 are true. Okay, so this is something that we have already seen in the earlier questions, and it's just a revision of that. So I won't go into the much detail, and then thus we will start assignment 7. So in weeks 7, category theory was defined, and it's based on the category. The entire assignment is on the category theory itself. So maybe we can just have a recall of what's the category, and then we will see the questions. So just give me a second. I will just define the category theory for you, and then start the questions. Okay. So yes. So for assignment 7, you first need to know what is a category theory. I will write the revision part. So the definition of category. So a category C consists of three things. First is a collection of objects of C, and second is, so we will use the notation obj, uh, maybe denoted by, I will write denoted by object C. Okay, and the second is for all objects A, B of C, a collection C of AB of arrows from A to B. So by arrows, you can just say some kind of relation is there between these objects, and you have from one object to another object, you have some assignment, and that assignment is we say arrows. So there for all pairs of objects, such an assignment is there, and this assignment is also nice in the sense that uh, for objects A, B, and C, if you collect three of the objects, a composition function is also there. A composition function C. So you have the collection of all arrows from A to B. You have the collection of all arrows from B to C, and then there you can take their direct product and map it to the collection of all objects from A to collection of all maps from A to C. So how is the mapping is? So if F is an arrow from A to B, G is an arrow from B to C, then you can simply, you should be able to map it to the to something G of G composed with F. So the composition is also there in these arrows. So that's the third property, and this third uh, properties are such that it satisfies the following two axioms. First is associativity. Associativity. So for all A, B, C, and D objects of C, you have the associativity in terms of their maps. So F is inside, F is an arrow from A to B, G is an arrow from B to C, H is an arrow from C to D, then so for all such pair, we have the following, that is H composed with G composed with F is same as S composed with G composed with F in C of, you have this. And the second thing is it also have some identity. So for all objects A of C, there exists identity of A belongs to C of A comma A. You can map A to A by a assignment, say identity of A, such that it plays the role of this assignment plays the role of identity map for all arrows emerging out from A to B, and this should hold for any B. And it is true in the other direction also, that identity of A composed with F is equal to F for all F that is emerging out from B and going to A. It plays the role of identity. There is some assignment for each A. So with that, we say that this forms a category, and as an example, you can consider first category of sets. So that we will denote by set underline. So here objects are, first thing is to look at the objects. Objects are sets, all sets, and C of AB contains all set theoretic maps in from a set A to another set B. Okay. And what is third? The composition. Composition of arrows is just the composition of set theoretic maps. Similarly, you have uh, so yeah, one more thing. So for these maps, the associativity is also there and the identity map is also there. So this forms a category. And similarly, one have the category of groups in which all the objects are groups. Maps are the group homomorphisms, and uh, so and also the composition is the composition of your homomorphisms, and there also the same thing is satisfied, the property A and B. So yes, similarly you have the category of rings, category of fields, and so on. Okay, so I hope that is clear. And now we are in position to solve the questions as well. Okay, so let me just paste first question. So yes. Mm, Now we are position two. So this assignment has comparatively easier questions, I will say. You just need to apply the definition of category theory, and uh, it will give you the solution. And yes, so the first option is, so first question is, let z denote the set of all integers, and n with a set of all non-negative integers, that is the set of all natural numbers. You have the function uh, sending any natural number to sorry, they are not defining what is this n, but they are saying the function maps n to n factorial. Which of the following collection of arrows in the category set does f lie in? So you have the category set, and one has to say what is the domain and what is the mm, codomain. So since n factorial is defined for natural numbers only, we are not uh, defining it for any integer, and so natural numbers only, and with that also and n factorial belongs to uh, natural number for all n belongs to n. Therefore f is from n to n, or you can enlarge your domain and f is from n to z also, you can write. Okay, because something lying inside n, that means it will also lie inside z. Nothing is a problem. So domain is uh, uh, n, but codomain you can take any n or z. There won't be any issue, because its range is inside n, but you can have a bigger set in the codomain also, na? There is no issue in that. So yes, there are two options which are going correct: set n z and set n n. And here the domain is z, so we are not defining factorials for next negative numbers. That's why third and fourth are discarded. Okay, so maybe we can see the second question now. Yes. So it says let Fi denote the category whose objects are finite sets and whose arrows are injective functions. How many arrows exist between 3 and class of 3 and 5? So this uh, notation n inside this Square brackets is the collection of the elements from 1 to n. So the question says how many, so we need to find the number of all possible maps from 1 to 3, because box square bracket of 3 means 1 to 3, square bracket of uh, 5 means 1 2 3 4 5. So we need to find this number. And so for each uh, number, how many choices are there? Yes, it says you just need to find injective functions. That is the point. So yes, number of all possible injective maps, I must write. Injective map. So it's injective means two elements of 1 to 3 cannot have the same image in 1 to 5. Okay. So let f, okay, so uh, it will be like this. So let f be a p n injective function from 3 to 5, then and f of 1 is some alpha belonging to 1 2 3 4 5. Then f of 2 can be anything except, it's not a good way to write, uh, then f of 2 is equal to some beta which is not equal to alpha, or maybe it's to be beta which belongs to this set 5 minus this alpha. So, and this implies f of 3 is has to be something gamma inside 1 2, I will use the shorter notation, that's easy to write. So 5 minus the set alpha beta, right? So thus we have 5 into 5 minus 1 into 5 minus 2 choices for f, right? Because alpha can be chosen freely, then beta can be anything except alpha, and then gamma can be anything except alpha beta. So there are these many choices. So this implies there are 5 4 3 60 choices for f, right? So first thing is the first method is this. Maybe I can write like that. This is the first method. Second method to look at it is like that. We want to map 1, 2, 3. Uh, yes, we want to map the elements 1, 2, 3 to 1, 2, 3, 4, 5 in an injective manner, right? In an injective manner. Means 1, 2, 3. Oh, maybe I will write it in a better language. That's not good. So we want to map the elements of this to 5 in an injective manner. So uh, let alpha, beta, gamma are respectively the images of are the images of 1, 2, and 3 under such a mapping. Then there are how many possibilities are there? So you choose. So this is for choosing 3 elements out of 5. So you can make it as a selection problem, and you need 3 elements in from the set 1, 2, 3, 4, 5. So which are the images of the elements from this 1, 2, and 3. So you have 5 C3 possibilities, and also 3 factorial. This is because uh, for the permutation inside each selection, inside each selection of elements, it's so this is why, because maybe just to say a bit. So 1 going to alpha, 2 going to beta, 3 going to gamma, and 1 going to beta, 2 going to alpha, and 3 going to so 2 going to gamma and 3 going to alpha are different maps, right? So you have the same collection of elements alpha, beta, gamma, the same selection of 3 elements from 5, uh, but still you can permute these elements inside, right? In 3 factorial ways. So there are 5C3 into 3 uh, choices, and then there are these many choices, and this is 5, 3, 2 into 3. So that is, again you will see 60 will come, right? So in any of the method you will get the same answer, because it's ultimately how you look at approach the problem. The answer is uh, going to be the same. Okay. Okay, so I will move to the next question if it's fine. So it says a partially ordered set, poset P is a set with a relation that is transitive. Means if x is related to y is related to z, then x is related to z for all x, y, z in P. Reflexive, if x is related to x for that is x is related to x for all x belongs to P. And antisymmetric means if x is related to y, y is related to x, then x equal to y for all x, y in P. So given posets P and Q, a function can be defined from P to Q. Uh, sorry, a function from P to Q said to be order preserving if uh, the order with respect to this poset is preserved. That is, if x is less than equal to y with this partial ordering, then fx is also less than equal to fy with respect to the partial ordering in Q. So P has a partial ordering and Q has a partial ordering. So if x and y are related in P in this order, then fx and fy is also related in the same order inside the image set, that is Q. Okay. So let poset be the category whose objects are posets. This bold poset is the category, and arrows are order preserving functions. So all objects are posets, and uh, so for two posets, what is the arrows? You map the elements from one poset to another poset by the order preserving functions, and those order preserving functions are the uh, arrows for those posets. Okay. So then the question is, how many arrows does poset 3, 5 contain? So, uh, uh, so this means the collection of, right, better way, poset uh, this, this is the collection of all order preserving the collection of all order preserving maps from this to this. So if f belongs to this poset, then f is a map from uh, the collection 1, 2, 3 to 1, 2, 3, 4, 5, such that f of, so 1 is less than 2, so f of 1 will be less than equal to f of 2, and f of 2 is less than 3, so f of 2 will be less than f of 3. So yeah, so how to then see the number of such maps? So from method 2 of the last question's solution, we get that there are 5 C3 many choices for the range set of F. Okay, so you collect three uh, uh, a set of three elements from set of five elements, and so the internal permutations might be there, but the range set will be same for a selection, right? So there are 5C3 many choices for the range set of F, and for each such collection, uh, there is a unique F, unique order preserving F, order preserving uh, possibility of F. Okay, and this is because if, say, uh, the choice of range set is some alpha, beta, gamma, then we need to define uh, F such that F of 1 is less than F of 2 less than F of 3, and range of F is alpha, beta, gamma. So if uh, so without loss of generality, if say alpha is less than beta less than gamma, then you have to define, then F of 1 has to be alpha, F of 2 has to be beta, and F of 3 has to be gamma, because you have to preserve the order. So that's how you have to define. Okay, so there are, so this implies there are just these many choices which are playing role. FC3, that is F factorial divided by 3 factorial 2 factorial, 10 choices for, okay. So there are 10 main choices for defining these order preserving functions from uh, the set 1 2 3 to 1 2 3 4 5. Okay, so let me just move to the next question. So fourth question says, let P be the power set of 0, 1 partially ordered by inclusion. Then in the notation of the previous problem, how many isomorphisms does poset P, P contain? So that's an interesting problem. So P, that is the power set of 0, 1. So how many elements does it have? The 2 raised to so power set of an set with n elements has 2 raised to n elements. So there is here n is 2, so it will have 4 elements. So first is 5, second is singleton set 0, then singleton set 1, and uh, then singleton set then the whole set 0 comma 1. So there are 4 elements, and it says then in the notation of the previous problem, how many isomorphism does poset p comma p has. So uh, partial order here is here, partial order is inclusion. So if f belongs to the poset p comma p, which is uh, then f is a map from p to p, preserving p to p, uh, preserving inclusions. Okay, so inclusions in maybe I should write inclusions in p. Yeah. So thus f of phi is equal to phi, and f of 0 1 2 0 comma 1 is 0 comma 1, since phi is the only set contained in every other set, and 0 comma 1 is the only set containing every other set. So there is no possibility for f which can map these two elements to somewhere else. So they have to be fixed, because there is no other set which satisfies the same inclusion relations as this set. However, also 0 set 0 satisfies the following inclusion relations. By the following inclusion relations, what are the following? It satisfies 0. Phi is contained in 0. It's contained in 0 comma 1, and 0 is not same as 1. We'll be writing this, and let's write this. So it satisfies this inclusion relation, right? And one satisfies phi contain in 1, contain in 0 comma 1 comma, again this is not the inclusion I should have written. So 0 is not contained in 1, and here for 1 is not contained in 0, right? So either we can fix 0 and 1 under F, or we can interchange them. Okay, so there are two possibilities, and thus uh, those possibilities are, thus F can be of uh, can have thus F can have one of the following form. What are those forms? So instead of writing form, I will write one of the following type. Okay, so F is from P to P. So let's say F is equal to F1 from P to P, sending phi to phi, 0 to 0, 1 to 1, and 0 comma 1 to 0 comma 1. So it's an order preserving, of course, and second possibility is F can be F2, which is from P to P, uh, sending phi to phi, 1 to 0, means 0 to 1, and 1 to 0, and then 0 comma 1 is fixed to 0 comma 1. So there are two such possibilities, and these are the all. Okay, so this implies there are how many isomorphism does P was at P comma P have? So thus poset P comma P has two isomorphisms. Okay, these are the two isomorphisms that F must have. So if F belongs to S, uh, I should write is an isomorphism, then because we need that it's an isomorphisms, otherwise we can just simply map it to a single element and then say okay, it will satisfy the uh, partial inclusion relation. Okay, so that's the end of question number 4. We can move to question number 5 now. So this is the smallest question that we can have, asking the smallest number of objects that a category can have. So this is question number 5. and the solution. So empty category with no objects and no arrows is vacuously a category. Objects and with no objects and no arrows is the smallest category. Is the smallest category. Thus, the smallest number of objects smallest number of objects uh, in a category uh, that a category can have is 0. Okay. So if the empty category is also a category, so um, there also all the assumptions of the categories are category is satisfied. So the smallest number is 0. Okay. Question number 6. I need to find. Yes. Consider the category logic, whose objects are logical propositions with single arrow from A to B. If A implies B is says that B is a logical consequence of A, composition in this category is guaranteed by which logical implication? So composition in this category means A implies B and B implies C, then A implies C, right? This is the composition that is there. So this composition is the logical implication is guaranteed by the transitivity. Clearly, this is because A implies B, B implies C, then A implies C is what we say it's transitive, right? So this is the transitive property of the logical implications. This composition is guaranteed by the transitivity property of logical implication. Okay, yeah, that's it. Now we can move to the question number 7. So 7 question says, given a poset P with partial order and CP with a category whose objects are the elements of P, and there is a single arrow from X to Y, if and only if X is less than equal to Y, and so this is the mm, partial order. This is the uh, arrow that is being defined in the category of elements in a poset. So given a poset P, now we are defining a category inside that poset such that uh, there are arrows from X to Y if and only if X is less than equal to Y. Okay, and if X is not less than equal to Y, then there is no arrow. Okay, so let P be the poset with at least 2 elements, then every arrow of CP is N. So first we will show the epimorphism. It's an epimorphism. Let F belongs to the arrow X and Y. Maybe let me write let X, Y, and Z are inside P. Okay, so if F is an arrow from X to Y and G comma H are from Y to Z such that GOF is equal to OF from X to Z, uh, then by the definition of the above category, what we can have? We know that there can be at most one arrow between any two elements of P. And there is it's saying that from G to H we have a arrow, means uh, so G has to be H, right? Because there can be at most one such thing, and hence F is a epimorphism trivially, because being an epimorphism means whenever you have G compose F to be equal to H compose F, then you have G equal to H, right? Now, monomorphism. So, this is similar to epimorphism because there is a single arrow again when you come to the there it will be F compose G same as uh, F compose H, and then you have to show that G is equal to H, but there is a single possibility for G and H, so they have to be the same. Okay. And for isomorphism, so it's not isomorphic because if X is less than Y, then there exists a single arrow from X to Y, but since X is strictly less than Y, so there won't be any arrow from Y to X. So thus it's not a it is not it is not a isomorphism. Okay. So since the converse in the converse direction, you may not even have an arrow, as in the case of X less than Y. So X is less than Y means there is a single arrow from X to Y, but from Y to X there is no arrow. So you cannot say that the inverse of the arrow from X to Y exists, right? Because there is no arrow in the converse direction. That's why it's not an isomorphism. So uh, first and second option are correct, but third and fourth are not correct. Okay. So let me just move to the next question. That is the eighth one. So it says for any pair of arrows from G from B to C and H from B to C, an arrow F from A to B satisfies G O F equal to H O F equal implies G equal to H, then F is necessarily monomorphism, epimorphism, and isomorphism, and none of the above. So uh, this is by the definition. By the definition, it is uh, an epimorphism, right? That's it. Also, each epimorphism need not be a monomorphism or an isomorphism. If it's not in a monomorphism, then it may not, it's sure that it won't be an isomorphism. So any epimorphism is need not be in monomorphism or epimorphism. There are many examples for that. Uh, Simplest one is consider the category of sets. Maybe you can consider, for example. There, every epimorphism need not be a isomorphism, or in fact need not be a monomorphism. Okay, so yes, I think we can move to the next question now, which is so it says let z plus 0 be the monoid of integers under addition and n plus 0 be the monoid of non-negative integers under addition. The inclusion map I from n to z is in the category of monoids is a uh, monomorphism, epimorphism, isomorphisms, or none of the above. So yes, so you have the category of monoids, and the inclusion map one has to see whether it's what kind of map it is, monomorphism, epimorphism, or isomorphism. So solution. So let's say I is the map from n to z. Then first we will check that whether it's a monomorphism or not. So uh, for all g comma h from A, let A be a monoid, then for all g comma h maps from uh, or maybe I will write it like that, let A be a monoid and gh belongs to uh, what's the notation that it's using for the category of monoids? Nothing. And let A be a monoid and g comma h be uh, the maps from be some maps, be any maps from A to N, uh, so with F I compose with G is same as I compose with H, then for any element A inside N, I compose G of A is what? So I over G of A. So it's an this is an inclusion. This belongs to N, right? And I is the inclusion map. So this is G of A. Since I is from N to Z, the inclusion map, and that is same as uh, and uh, I compose H of A is I H of A, which is H of A again, and this implies GA equal to HA for all A belongs to A, and this is since I compose G is same as I compose H, right? And I compose HA is HA and I compose GA is GA. Okay, so and thus Z is equal to H. So it's a monomorphism. Second thing, this implies I is in the inclusion map from N to Z is a monomorphism. Yes. Second, we have to see the epimorphism thing. So here we wanted to show that GOI is equal to HOI implies G is equal to H for maps G comma H from Z to A, right? Here codomain is Z. From Z to A for any map from Z to A, we need if GOI equal to HOI implies G of H for maps GH from Z to A, where A is any monoid. Okay, so this is a bit tricky. So let's say thus we need to show that GZ is equal to HZ for all Z belongs to Z. Okay, so for that now let Z is greater than equal to I'm using bad notation. Let Z is greater than equal to 0, then G compose I Z equal to H compose IZ. This is given, and this implies G compose. So we need to show this. If GOI equal to HY, then GH G equal to H. Okay, so GOI is Z equal to okay, I will consider like that. Since GOI is equal to HY as maps and I from N to Z is the inclusion map. So therefore GOI Z is ZZ and HOI Z is simply, oh, again I'm using bad notation for this Z. I should use the same notation. So it is GOIZ equal to HZ and HOIZ equal to HZ for all Z inside, um, for all Z greater than equal to 0. And the second case is when Z less than 0, we have to actually apply some trick. So what we will do, so GZ is equal to GZ uh, star 0 bar. So what is this uh, 0 bar? This is additive identity, maybe just identity I will say, because it's a monoid identity in, so G is from Z to A. So it's the identity in A. Okay. So and H, H is also from Z to A. So this you can write that star H of 0, because H of 0 has to be 0 if it's a monoid morphism. Then H of Z is nothing but H of minus Z plus Z, and by monoid homomorphism it should uh, split like that. It should distribute, and this will give you HZ, H of Z. And since Z is less than 0, therefore minus Z is greater than 0, implies G of minus Z equal to H of minus Z. We will use this thing here, maybe I can write. So this will give you G of Z, G of minus Z star H of Z, and that is G of Z minus Z star H of Z, that is G of 0 star H of Z, and G of 0 is the 0 bar in H in A, and it's applying on HZ will give you HZ. Okay, so this implies that I is an epimorphism as well. Now, yes, uh, third part is to check whether it's an isomorphism. Clearly, I is not an isomorphism because it has no inverse. Okay, so uh, that's why we just have epimorphisms and monomorphism, but not an isomorphism. So maybe we can move to the next question now. An arrow that is an monomorphism and an epimorphism is an isomorphism. So this is false. Same. So false. And why it is so? For example, see question number 9. Okay, there it was an epimorphism and monomorphism, but it was not a isomorphism. Okay, so that's a straightforward application of question number 9. Question number 11. So it's also a simple question. Says which of the following are always holds in every category. A composition of monomorphism is a monomorphism. A composition of epimorphism is an epimorphism, and a composition of isomorphism is an isomorphism. So A and B, A, B, C are correct by the definitions of. So one just have to use the definitions of them, and it will follow easily. Isms, epimorphisms, and isomorphisms. Okay, so it's just as applying definition and nothing else. Okay, so I will move to the question number 12. We have just 10-15 minutes more, so I will try to finish this assignment today itself so that we can start assignment number 8 in the next session. For every category C with an initial object 0, and for any object A of C, the unique arrow 0 to A is always uh, always a monomorphism, epimorphism, isomorphisms, or none of the above. So for 12, solution is, so we have to see first, let's see the monomorphism part. So the category has initial object 0. So one can consider the category of rings, then Z is an initial object, and the map sending Z to the 0. So this is ring with 0 elements. The singleton 0 I will draw, and the map is not a monomorphism. Why is it so? Because uh, this is because uh, if G and G comma H are from uh, so for monomorphism, what you need that this thing, right? uh, if G and H are mapped from some category to the domain, then I compose G same as I compose H. F compose G same as F compose H. If you have to check that F is a monomorphism of or not. So if GH belongs to the map, if GH is a map from say some R to Z, are ring homomorphisms for a ring or any ring R with f of G is equal to f of H, uh, then see, this we even don't need uh, with R, then f of G uh, is equal to f of H is equal to uh, the zero map, because G, whatever value G take, and then F will map everything to zero, right? But uh, G and H may not be equal, right? You can define G in any way. F of G is f of H for any G and H. So in general, it holds for all G and H. So you can define any GHN such that they are not equal, but still f of G will be same as f of H. Okay, GHH may not be equal. Thus, uh, F may not be a, thus F is not a monomorphism, right? Now for epimorphism, we define the map from consider the category of groups, then identity. The group with single element is the initial element, initial, and as well as the final terminal object, initial as well as the terminal object. And for any uh, G belongs to object of uh, uh, maybe I will denote it by category of this is just by say C. Okay, so for any G belongs to object of this category, the homomorphism G not equal to identity, I will take G2. G is not a epimorphism, right? Because G has more than one element, and uh, identity has one element, so it cannot be a epimorphism. So epimorphism is also not there. And the third option is isomorphism. So it's not. Uh, this implies. So it's not an epimorphism, monomorphism. So it cannot be an isomorphism because each isomorphism is an epimorphism, is a monomorphism. So only D is correct. Okay. This implies option D is correct. Okay. So yes. Then let's move to the next question. So it says let P be be a poset and C of P be the corresponding category. Which of the following of two elements? Which of the following is the product of two elements x comma y in this P? So x, uh, uh, this notation y, the least upper bound of x and y or the greatest lower bound of x and y. Okay. So P is the poset and CP is the corresponding category. So let me first define what is a product. So product is the element x cross y such that it maps it has maps uh, it has maps to maps sending it to x and y. So if x cross y can be mapped to x in the category of P, then when an element can be mapped to another element in the category of poset when that element is lesser than the other element. So x cross y is mapped to x in CP means x cross y is less than equal to x. Okay. And similarly, if x cross y can be mapped, I should write also if, because we already have that there are just maps. So yeah, also if x cross y can be mapped to y in CP, then x cross y is less than equal to y, and thus x cross y is less than minimum of x comma y, and in addition to that, if any element z is less than equal to x and z is less than equal to y, then we have the universality condition for the products, universality criteria for the product x cross y that implies that there exists an arrow from z to x cross y, and which implies z is less than equal to x cross y, and thus x cross y is the greatest lower bound of x and y. Okay, so this is the greatest lower bound of x and y. Okay, okay, so second option is correct while the first is not. So we will move to the next question. That is the second last question of this assignment. It says which, oh, let me just paste the question first. It says which of the following categories do not have products. So it has Cartesian product, that is the product that satisfies the condition of product, and it has direct product of groups, so that will satisfy the, and here you have direct product of monoids. So the only option that is left is CP for an arbitrary poset. Okay, so why is it not so? Because arbitrary poset P may not have the greatest lower bound. Okay, so I leave it to you to just verify the details. Okay, so this is verify details. Yeah, we'll just leave it to you without mentioning anything. We just need to say why it won't have the product. Okay, so question number 15, I will quickly explain, and then we will stop the session here. Okay, so it says let S be the empty set of objects in the category set. How many elements are there in product of X? So this says, so this is a collection of arrows. This is what? This is just product, right? This is a collection of arrows pi x to each element x belongs to S, such that for any set y with a collection of arrows, there exists a unique arrow from y to x, right? This is what the definition of product says. Now since S is empty, we have only the second property. We have only the property that for any object y, there exists unique uh, for any y, I will say, not object, for any y there exists a unique map from y to x, right? And this implies that x is a terminal object in set, the category of set. And that implies X is a singleton set, because the only terminal objects in the category of sets is the singleton sets. Okay, so because these are the only sets which have single arrows for each and every element of from each and every object of the set from the sorry, from each and every element of for each and every object of the category of sets. And what are the objects in the category of sets? That are the sets. So these are the only sets which have single arrows from each uh, from every other set. Because if you have two uh, what to say, if you have a set with two elements, then you can define more than one possible maps from any other object. For example, if you have say the set with two elements x comma a comma b, then and y is any other object with say three elements, then you may map c here and d and e here through one, or uh, the second map you can define is you can map b here and d here and e here. There are many ways, but if there is only a single element, b is not there, then you have to map all the elements of the other sets to the single element only. So if you want to have a single map for every others from every other object, the only possibility is the set is a singleton set. So that's why the terminal objects are just the singleton sets in the category of all sets. Okay, so with that, I will stop here, and we will have our next session on uh, the 26th is uh, Tuesday. So that session is preponed today, and then we will have the next session on, I think, 2nd of April. That is the uh, uh, Tuesday. I will just confirm it. So yeah, so next Tuesday is on 26th, but that session is preponed to today. So we won't have session on 26th, and uh, the then we will have the session on the next Tuesday, that is the 2nd of April. Okay, so I will write it here also, that next session will be on 2nd/4/24. Kathy, do you want to say something? Some noise is coming. So,
No, no, no.
okay. So the next session will be on 2nd April 24. That is Tuesday at our usual time. That is 6 p.m. Okay. Okay. So I will stop here. See you in the next section. Okay.
Thank you.